So in this section, I'm going to continue with further discussion on normal subgroup. And I'm going to show you a few important results. I'm also going to prove these results, because actually these results are not considered as a theorem at the time of examination. They are considered as a problem. Okay, so but I shall state the result as a theorem, and I'm going to prove these results. They are very simple, but they are very useful in dealing with problems of group theory related to normal subgroup. Okay, so my first result is this. It's a theorem, and it is saying that let capital H be a subgroup. Let capital H be a subgroup of a group capital G, of a group capital G. Then the following conditions are equivalent. The following conditions are equivalent. What are these conditions? Number one condition is H is a normal subgroup. This statement is equivalent to the following statement, that is 2, that small g multiplied by capital H multiplied by inverse of small g is a subset of capital H for all g belonging to capital G. And this in turn is equivalent to the statement G H G inverse is equal to capital H for all g belonging to capital G. So I'm going to show you in this class, first of all, that these three statements that I have written, they are equivalent. And then I'm going to tell you why these results are useful. Okay. So proof. In the proof section, let us begin with showing that the statement 1 directly implies statement 2. Okay. So let small g belonging to capital G. Let small g is an element of capital G. And in statement 1, we have assumed that H is a normal subgroup. So since H is a normal subgroup of capital G, and we know if it is so, then AH equal to HA for all A belonging to G. If H is a normal subgroup, if this happens, then H is a normal subgroup. Okay, so since H is a normal subgroup of G, we are considering an element of capital G. We denote this element by small g, and for that we must have GH is equal to HG by definition of the normal subgroup. Hence, for any small h belonging to capital H, GH, the element GH will belong to the set which is a left coset generated by G. So GH, the element of the form GH will belong to the left coset GH. But we know from definition of the normal subgroup and the condition given in the statement 1 that GH is actually HG, because we have already mentioned it over here. And so the element GH can be expressed as H prime into G for some H prime belonging to capital H. Why is it so? Because we have seen that GH is belonging to the left coset GH, but left coset GH is equal to the right coset HG. So the element GH can be written in the following manner by the definition of the left cosets and right cosets. You know the elements will be of the following form. So we can find out an element in the subgroup H, which is denoted by H prime, where GH can be written as H prime into G. Now, GH is equal to H prime into G, and we can multiply both the sides of this equation by G inverse. We can multiply both the sides of the equation by G inverse, and we can associate these two. Okay, which implies that it becomes H prime only because G inverse is the identity element. And therefore what we have got that G inverse is actually nothing but the H prime, the element H prime itself, which belongs to capital H. But we know that the element of the form G inverse belongs to the set G inverse. And we have found that this sort of element G inverse, this sort of element also belongs to capital H, and which is true for all G belonging to G and for all H belonging to H. Okay, and this implies the set G inverse is subset of capital H. So we started with this condition 1, that H is a normal subgroup, and we have got the condition given in equation in serial number 2, which is saying that G inverse will be the subset of H. Now I am going to show the second part, that the statement 3 is directly implied from the statement 2. So in statement 3, we are actually assuming that let G inverse is a subset of H for all G belonging to capital G. This now becomes my condition, and I'm going to check whether the condition given in statement 3 follows from it or not. Okay, so let us consider an element H belonging to capital H, and then by the given condition which I have assumed over here, G inverse H G inverse that will belong to the set G inverse H G inverse, which is a subset of capital H. Carefully observe what I have written. I have written that this is the set which is a subset of capital H, and it happens for all G belonging to capital G. We have considered an element H in the subgroup capital H. Now, as it is written that this result holds for all G belonging to capital G, inverse of G is also an element of capital G. So in place of all the G's over here can be replaced by G inverse. So in place of G, I am putting G inverse. In place of G, I am putting G inverse, and that's why I am getting G inverse H, G inverse of inverse. This becomes another set. Its element will obviously be of the following form. This sort of element will definitely belong into the set that, and this sort of set is a subset of capital H. So everything which I have written over here follows from the condition. Now I'm going to the next page. Take a screenshot. Now, after that, hence, if I multiply both the sides of the element, G inverse HG, if I multiply both the sides of the element G inverse HG by G and G inverse, from left I am multiplying by G, and from right I am multiplying by G inverse, that will obviously belong to the set GH G inverse. And so H belonging to G H G inverse. Thus, what we have found? We have found from our discussion that H is a subset of GH G inverse, which in turn is a subset of H. And that implies GH G inverse is equal to H, which is the condition given in statement number 3. Now, the last part of the problem. I'll start from the statement 3, and I will try to find out whether the statement 1 directly follows or not. So if I write the statement 1, 2, and 3 in the following manner, so some kind of cycle is being formed over here. And if this kind of cycle can be shown, then we say that the statements are equivalent. Okay, so that is what this structure is actually being followed in the following proof. Since GH G inverse equal to H for all G belonging to capital G, this is the condition of statement 3. Then we find that GH G inverse into G is equal to H into G, and this implies GH G inverse G is equal to HG, and that implies GH equal to HG for all G belonging to capital G, which implies H is a normal subgroup. And hence we have proved the given cycle. All the statements which are written in the theorem, they are equivalent. What is the purpose of the given theorem? Suppose we are given a group, capital G, and a subgroup is there. Subgroup contains many elements. Okay, and if you want to show that all these subgroups, if you want to show that this particular subgroup which you have constructed is a normal subgroup, then you have to select each and every element of G, and that you have to show that this element of G is actually commuting with each and every element of the subgroup itself. Sometimes it becomes a very tedious task to do, and therefore we can use to show that a given subgroup is a normal subgroup. We can either use statement 1, or we sometimes try to take the help of statement 2, or sometimes we try with statement 3. The theorem is saying that to show a given subgroup to be a normal subgroup, any of the process depicted in statements 1, 2, and 3 can be used for our purpose. Okay, and that's why this particular result is so important. Now, the thing which I'm going to define is the following. And this particular thing which I'm going to explain right now is nothing new to you. First encounter of this particular result were made in first semester when you studied vector space. I don't know who were the teacher then. If the teacher taught you about that, then probably you knew. If you have not come across this thing earlier, then I don't have to say anything about that. Then this is the thing which is I'm going to talk about right now is a new topic to you. But you have come across this, if you can remember that you have done it in the chapter of vector space, then this thing which I'm going to explain is nothing new. So in vector space, you are supposed to come across the term which is called quotient space. I don't know whether you are familiar with this term or not. Here I'm going to explain a similar term which is called quotient group. both the structures of quotient space and quotient group are similarly obtained, similarly found. The way by which they are actually found in both the spaces, vector space is a kind of algebraic structure, group theory is a kind of algebraic structure, field ring are kind of algebraic structure. So in every algebraic structure is defined by certain rules that the elements of the structure, the elements of the set in the structure must follow. So everything which I'm actually deducing here at this moment with respect to the structure called group theory, similar things can also be deduced in the structure called vector space or ring or field. So if there is a concept like quotient space and quotient group, there are concepts like quotient ring and quotient field. So I'm going to talk about quotient group right now, and for which we need a theorem. Let capital H be a normal subgroup of a group capital G. Okay. Denote the set of all cosets AH slash A belonging to G by G slash H. Don't read this part as G by H. A set cannot be divided by a set. You can, if you want to read it, you can read it as G slash H. Okay. So we are first considering a normal subgroup. Therefore we started with a normal subgroup because the concept of normal subgroup has to be clear before we come across the concept of quotient group, because the concept of normal subgroup is required in defining the quotient group. So we just don't have to consider any subgroup, but we have to consider the subgroup of the type which are normal. And we consider the set of all cosets. Especially here we are considering the left cosets. And we are defining this set by the notation G slash H. Now, remember that I am not naming this set as G by H. I mean, G by H contains all such left cosets in it for all elements of G belonging to capital G. So if you have left, if suppose there are 3 elements in group A1, A2, A3, in G by H, there will be elements like A1H, A2H, A3H. If there are 10 elements in G and you consider this normal subgroup H, then in G by H, we have the elements like A1H, A2H, A3H, and in this manner, A10H. So G by H elements, the elements of G by H will be of this form. And we define an operation star on G by H. Right now we have defined a set over here whose elements are left cosets. But this set has, if you want to show that this set is a structure, is a space, or is a group, then you have to define some kind of algebraic operation on that. So that algebraic operation is defined to be star, and it is defined as the following: for all AH, BH belonging to this set G slash H, AH star BH, this should be equal to ABH. Our task is to show that this, first of all, that G slash H with respect to this operation is a group. We need to show this first of all. First of all, you need to show that this result, this particular, if I consider this set and this kind of operation, together they form a group. I'm going to prove this particular, I'm going to show that this structure is a group, first of all. Then after that, I'm going to define the quotient group. Okay, so let us deduce the property of the group one after another. Okay. So in proof, I'm writing our first and foremost, just a minute. Our first and foremost task is to show that the operation that has been defined in the previous page is a well-defined operation, well-defined binary operation. If we can show that it is a well-defined binary operation, then automatically the closure property of the group will be satisfied. So first of all, I'm going to show that it is a binary operation. In other words, we must show that if AH is equal to A1H and BH is equal to B1H, if I consider this kind of things, then we need to show that ABH is equal to A1B1H. Because why I want to show this? Because if I can show this result, this will prove that AH star BH is equal to ABH, which is equal to A1 B1 H, which is equal to A1 H star B1 H. Carefully see all the lines that I have written. I know, students, this topic is so abstract that sometimes probably you are losing the interest, but believe me, what can I do? Because if you want to know this topic, even if you don't like, you have to digest it. I know. Before I proceed, I'm giving you some time to look at or copy what I am writing over here. But meanwhile, I must say this thing, just keep in mind, I am a teacher of mathematics. So probably these things are very important to me. I can find it, I can see its, I can follow its logic, I can see its application, everything. But you are in a position where I cannot judge you. I cannot I cannot place you in my position, because definitely you are students and your experience is not matching with my experience. So probably you are not following it properly, or you are missing its logic, or you are not seeing its application. Maybe after 3 to 4 years, a very few students of this class will find that, yeah, some applications can be seen here and there. But since the topic is there, and since the topic is so abstract, you have to dedicate a considerable amount of time to study it, because no other way out. I do not know any other shortcut methods by which this topic can be taught. Okay, some other teachers who are more experienced, then they probably know how to do this. But seriously speaking, I do not know any shortcuts. So whatever I am showing you, Either you have to love it or you have to digest it. Okay. So this is my objective. Now, AH equal to A1H and BH is equal to B1H. This implies that if this happens, because I told you that I will start from here. Okay. So if I consider that AH equal to A1H and BH equal to B1H, this implies that the element A is equal to A1H1 and the element B is equal to B1H2, where H1, H2 belonging to capital H. Isn't it? So if AH, the element A, which is the element of the group, it is constructing the left coset AH, and your left coset is equal to the left coset constructed by the element A1. Okay. Now in AH, you will find an element like small a. Carefully observe. Probably you are missing this term. I'm explaining this. AH and A1H, they are same. Now in this A, in H, since H is a subgroup, H will, you know that if capital G is the group and H is the subgroup, then the identity element of G is belonging to capital H. So if you want to construct AH, then you have to consider the element E also, which resides in H. So we must find an element of the form AE, because AE will belonging to AH. And what is AE? AE is A and it belongs to AH, isn't it? So if we take an element A from AH, and since AH equal to A1H, then there exists some element H1 in H for which A can be expressed as this, A1H1. That's why I have written, because of this. And similarly, B can be written as B1 into H2 with respect to the same logic. Now, A1 B1 inverse AB, a very important result. I don't know whether you have solved any exercise from the book or not. An important result was there. You can find it in the book in the first chapter of group theory, that AB inverse is equal to B inverse A inverse. I can't recall whether I discussed it in the class or not. So I'm going to use this result. So A1 B1 inverse multiplied by AB gives us A1 B1 inverse means B1 inverse into A1 inverse into AB. And this is equal to B1 inverse A1 inverse into A1 into B. And this can be written as B1 inverse A1 inverse into A no, I shouldn't, just a minute. I have to, not in this manner. I have to write it in some other way. First of all, I'm writing it as B1 inverse A1 inverse. I will not associate the numbers. Associating the numbers will not do any good to my calculation. So B1 inverse A1 into AB. If I write so, then in the next line I can write it as B1 inverse into A1 inverse, and this AB, in place of this AB, in A can be replaced by A1 H1 and B can be replaced by B1 H2, just like we assumed over here in the previous line. Yeah, now it is all right. Now we can associate this Now we can associate this A1 inverse A1. Okay, so and the rest will remain same, and from there we actually get B1 inverse H1, B1 H2. So this is number one. Since H is a normal subgroup, H B1 is equal to B1H, and hence H1 B1 is equal to B1 H3 for some H3 belonging to capital H. Okay, hence from 1 A1 B1 whole inverse multiplied by AB gives us B1 inverse B1 H3 into H2, because in place of H1 B1 we have substituted B1 H3, and which is H3 into H2. Obviously it will belong to capital H, because H1 H3 belonging to capital H, H2 belonging to capital H, and therefore H3 H2 will belong to capital H. This implies that A1 B1 H is equal to AB H. Okay, just quickly take the screenshot because I'm going to the next page. Hence AH star BH is equal to ABH, and this is equal to A1 B1 H, and which is A1H star B1H, and so star is a well-defined binary operation. Okay, next we show that star is associative. Let AH BH CH belonging to the set G/H. Now AH star BH star CH can be written as AH star BCH. I hope you are following me. This is equal to ABCH. That can be expressed as ABCH because ABC are associative. They are elements of the group. So we can rewrite them as ABH star CH, and this can be written as AH star BH star CH, and hence star is associative. Hence star is associative. Now EH belongs to G by H or G/H, and if I take the composition of AH and EH, this can be written as this. AE means A. Again, A can be written as EAH, and this can be written as EH star AH, and which is true for all AH belongs to G/H. This shows that EH is the identity element. Of G/H. Again, for all AH belongs to G by H, A inverse H also will belong to G slash H, and AH star A inverse H can be written as A inverse H, which is equal to EH, can be written as A inverse A into H, and that is A inverse H star AH. Thus, AH belonging to G slash H for all, AH belonging to G slash H, A inverse H is the inverse of AH. So see, all the properties of group are actually being satisfied over here. We have shown the closure property over here. This is the closure property, if you think. Then we have also shown that associativity holds. We have shown that identity is there. We have shown that inverse is there. All the properties are satisfied, and therefore from there we can conclude that G slash H star is actually a group. Is actually a group. And such a group, now I'm going to write the definition finally. Definition is let capital G be a group and H be a normal subgroup of capital G, then the group G slash H of all cosets of H in G under the binary operation AH star BH is equal to ABH is called a quotient group or a vector group. It's a very important definition. You can ask me, why did you take the pain of, sorry, this is page number 3. Why did you take the pain of doing this calculation in details? Because in the online examination, you may encounter online examination. Oh, sorry, this is page 1. In online examination, you may encounter encounter the questions with respect to the quotient group. They may ask you small questions like this: what are the inverse element of quotient groups, or what are the identity element of quotient group, and so on. So this result is actually very important. So with this, I'm going to conclude my today's session. Tomorrow in our scheduled timing, we are going to continue further on these topics. Hope you have taken the snapshots. If you have not done, please do so. This is page 1, page 2, page 3, page 4, and page 5.